Ah, interesting, interesting. Dangerous but interesting. Is there a little bit of a bias in terms of backgrounds of folks or specialization? Is it more like an ML crowd or more a formal reasoning crowd or anything like that?
Uh, well, so not not automated reasoning. It was more on their LLMs kind of stuff. But
Interesting. Yeah, interesting, interesting. Yeah, that'll be, I guess, nice for a couple of deep dives, just because also be interesting to discuss, because we have a couple of follow-up ideas and some directions to go. And on some, I'm rather jaded, so it's good to maybe get like a bit of fresh enthusiasm. But yeah, we'll see. Hmm. Hmm. I'd be surprised, but who knows? Who knows where this is talking? But yeah. All right, very good. In that case, let me just share my screen with a couple of slides, not too many. Again, as I said, probably mostly discussion based, hopefully. There we go. Does this work? Let me try that out. It's a new laptop, so one might break at any point, but we'll see how far we get. Okay. Okay, so everybody can see my screen. Okay, that's nice, and I can scroll back and forth. Okay, excellent. So yeah, topic today, Logic.py. This was our NeurIPS 2025 submission in December. The topic at the time was trying to empower or improve LLM performance using formal reasoning, and this is going to be the main hypothesis, and sort of the main motivation behind this is to see tool calling not just as a means of obviously interacting with components that you need to interact with, but actually as a core piece to improve performance, delegating tasks that obviously obvious tasks that you think the tools might be performing better at than the LLMs. The obvious example would be like using SymPy for math calculations, stuff like that. But our motivation was that we think way too many reasoning tasks, way too many steps, planning tasks, fundamental to many training tasks in modern LLMs are still being done by the network when they should be delegated. And we're sort of trying to motivate people to think not just in terms of what they need to interact with, but actually just in terms of planning tasks and reformulating their entire problems for LLMs as they can be solved more easily. That's also going to be actually the topic of the talk at AI later this year, where it's exactly about the same idea that you should actually start training your models and your entire agentic systems with these capabilities in mind that you actually need, and reformulating your problems with tools that you have available in mind. So before I get started into the actual Logic.py system, just a few words about my co-authors. Obviously, well, a lot of this is a bit outdated. Obviously, myself, my name is Pascal, and I used to work at Meta at FAIR up until recently in the what is now the coding capability team. So this was the coding team in FAIR, the research team, which published the Code World model for those who might have caught up on that. This is now sort of being, I guess, integrated into the whole superintelligence labs at Meta. And there was sort of the point where I decided to switch as well to Microsoft now, where I'm a member of technical staff, because The research component was a bit being deprioritized, which is usually a good sign that the coding model actually works and is something that will be useful for the new model. But since research is no longer a priority, I thought I might as well pursue some other opportunities. The lone survivor of our group, Peter O'Hearn. Some of you in the FM crowd might have heard of him, of course, mostly for his work on Infer. Has been a long time Meta employee, briefly in startup at Lacework. And he's still the only survivor. He's still at FAIR. He's still in that group, still focusing on research. And the final one, probably the person with the actual real ML and LLM background is Ricardo Cabral. He is also no longer at Meta, actually. He's now at NVIDIA, I think in a staff research position there. And his background is mostly in agents, where this combination came from. I was working in Ricardo's group at the time at Meta. Before I switched to FAIR, there was in GenAI while it still existed. And that's how we ultimately got talking about, could we actually integrate these solvers with their capabilities into these agent loops, and what can they actually do? It was nice to approach most ML folks and realize, well, these tools can not only be used for verification, for checking certain formulas, but also in a synthesis fashion, where we create solutions for problems that we give them. And that's how this whole Logic.py story got kicked off. Oh, nice. Yeah, I mean, that makes a lot of sense, because I was working with Peter in Lacework as well, actually, briefly though, and the static analysis crowd there was quite detached from the rest of the companies. So it was its own little startup. So it makes sense to be more interested in his research. Frankly, I think he was more interested in his research than the rest of Lacework, for that matter. All right, so the problem that we were looking at in this particular paper is about reasoning, or in this case, puzzles. And the kind of puzzles that we looked at were, among others, these zero logic puzzles. For those not familiar, these are usually just constraint satisfaction puzzles, where you're giving a setting, a domain, in this case, houses, or it might be any other possible assignment, where each slot might have different properties that need to be satisfied. And there's only certain valid values for each property in this context. So we usually always have a base setting, then the basic domain being specified, what are the valid phones, what are valid book genres, etc. And the basic pattern of these puzzles, at least in zero logic bench, which is one to be evaluated against, always remains the same. And then you have an increasing list of clues, which of course are your constraints in terms of indirectly specifying which person lives in which house and what kind of models do they use, etc. And the intent behind this benchmark is, of course, to force the models to go through longer and longer chains of thought and chains of reasoning, where they have to derive from these clues implications. And usually that's when especially with larger puzzle sizes, even if they, from a combinatorial perspective, don't get that much trickier, is usually where these models start to fail. And our hypothesis was, this obviously seems like a prime example, maybe even a bit too curated example, where these constraint solvers could come in. And the core intent there was, again, instead of having the model solve this problem directly, can we rephrase the problem? Can we reformulate it and have the model solve a proxy problem, which allows it to use a tool, in this case, an SMT solver, an SAT solver, depending on the problem. We had, as backends, we'll see that later, we had multiple backends, and in Polymath, which is the agent that we created for this paper. One is effectively CBMC, which we just use as a convenient API for SAT. And the other is a direct SMT backend, which I, in hindsight, regret creating. It was a bit of a decision of having to whether we would use CBMC's SMT backend or creating one directly. And the decision was that CBMC's SMT backend was a bit opinionated when it came to quantifiers and things like that, because it only supported things that really made sense in the program analysis that CBMC was interested in. So I decided I would just implement the SMT backend directly using like a very simple symbolic execution engine. And then I sort of realized or remembered just how that usually can be a death by 1,000 cuts, where you have so many small problems like that really matter in this context. That surprised me, like constant propagation, for instance. Small issues like these were a huge issue that actually caused huge performance problems. And so in hindsight, one takeaway from this paper is definitely that whatever tool you're using for reasoning should be based on a strong, robust engine that's not just a solver directly. It's possible and it works, of course, but these tools do a lot of things that are extremely helpful for these use cases as well. So just for completeness, this would be a solution for the puzzle just before. So the model has to fill these slots, and they would usually be scored in two ways. Either in the zebra logic bench, how many solutions were correct entirely, and the cell score where just would be partial scores in terms of how many cells in a puzzle were filled out correctly. The second intuition that I just wanted, obviously, is probably not that novel for the FM crowd here, but certainly for a lot of problems that we tackle in FM is this asymmetry that solving the problem itself, either, for instance, in this case, sorting a list or writing a sorting algorithm, even the most simple, most basic sorting algorithm that you could think of, is usually more complex. Certainly performing the task itself, certainly sorting a list of size n or whatever is more challenging for a model, depending on the size of the list, of course. And writing the usual escape hatch, writing a Python program that sorts the list for you is still more complex than in the case of static or formal reasoning, just writing a verification condition in CBMC or in any other VC you could imagine that verifies whether the list is sorted. It's something I think that folks that work with these static analysis tools realize when playing with them that this can be a shorthand, a quick and easy tool to sometimes just specify the problem, and then have the solver obviously being excellent state exploration machines explore this for you. And yeah, this just sort of demonstrate that the verification condition for sorting is usually extremely simple, can be a one-liner, and is much easier to understand for the model than writing an algorithm or writing a sorting algorithm. Of course, I guess a sorting algorithm is a bad example because models will have a million of them in their in distribution, so they would of course be perfectly able to do that. But just as an intuition of the problem or problems becoming simpler if we just have to specify a desired solution and what a desired solution looks like, rather than producing a solution or even more challenging, coming up with an algorithm that does produce that solution for you. This intuition we took into this agentic approach that we have. We call it an agentic approach. I mean, ultimately, it's fairly opinionated in the sense that the model doesn't actually have any real choice over which tools it wants to call at which point. But instead, this one is a puzzle-solving agentic setup that gets invoked by the model if it sort of detects that it is in a domain where this can be useful. So you usually have like a main model that would give the answer, but then it might delegate to the sub-agent. And the idea here is based on mostly informed, of course, by the structure of the zero logic bench puzzles. But this works with all other puzzles. In point of fact, when we were in NeurIPS review suggested that we try out other puzzles, whether they can get formalized just as easily, like linear constraint puzzles or Sudoku, even all these things, fairly straightforward puzzles. And even the nice insight that we had there is, even though we never planned for those puzzles, the infrastructure that we had planned for this was flexible enough that we could actually, without any code changes, just change the prompt was sufficient to solve those puzzles as well. So the first step here is and sort of differentiate between, I guess, natural language LLM steps versus deterministic formal reasoning steps and static analysis steps that we have. But the input is usually just any form of puzzle, a user input. And in the case of a benchmark, an expected output format. In the case of a user input, that's usually empty or just suggests just present it to the user in the most understandable fashion. But for zero logic benches, it would be like some JSON format that the answer needs to be in. And step number one is, since especially symbolic bench, since the domain and the constraints are quite separate from each other, we sort of separated the generation of the Python code as well into two stages. The first one is defining a solution. Irrespective of what the correct solution is, just define what does a solution actually look like for this problem, and how would you in the most compact way express that in Python. So the result of this would usually be just a Python class that comes out of this. And the model completely ignores at this point any sort of like the actual puzzle itself or the constraints, but just about what are we actually producing at the end of this. This is step one in the polymath agent. Given this data structure and still the puzzle information itself, we then move on to the next stage. So now it's just about mapping the puzzle constraints or the game rules in case of Sudoku, in case of Frogger, or any of the other puzzles, to constraints in Logic.py. Logic.py is ultimately just a sort of a Python superset where we added additional features like assertions, like non-determinism, etc., to make it easier to express constraints like these for these common puzzle like CSP problems. But ultimately, this became just front-end, additional front-end for CBMC or for SMT, although the mappings are quite different between them. With this information in mind, we would just then generate a validation function that would just apply all of these constraints, and then it would just be an existential query to CBMC or any of the backend. Is the solver input language libsmt2? For the so not for Logic.py, for the backend solver, for Z3, yes. So when we had SMT solver, we used SMT2, but we effectively just generated SMT2 formula. We didn't actually link against libsmt2 or anything like that. And that's how CBMC does it as well. Just generate the formula and send it to scdin of Z3. So converting to a solver language, again, for CBMC, this usually meant generating C programs with a couple of macros for just useful things that occur frequently. We had a couple of additional say features in the language that make it easy to express certain constraints. That was also the main goal. I mean, when we designed Logic.py, goal number one was that it should be as robust as possible. So it is Python. The assumption was that models would be able to handle Python fairly well just by default. But also, for instance, like type safety, we explicitly allow the model to reuse variables if it wants. We don't require it to declare types, etc. We perform type inference on everything, and so long as everything works out in the end, we're happy with that. Effectively just sort of removing any syntactic issues, etc. And at the same time giving useful shorthands for things that occur frequently, which we sort of borrowed from various languages. For instance, expressing uniqueness of a property. If you have in the data structure generation phase, if you have an ID property that should be unique across all instances of that property, that's basically just an additional annotation that you can create in Python and doesn't require any explicit hard-coded constraints that the model needs to come up with. And we have a bunch of those helpers to sort of make it easy to express common constraints. And obviously that goes into the same theme of Logic.py to make it as easy as possible and as robust as possible to express all of these problems, while at the same time being fully flexible. At the end of the day, if the model wants to create custom constraints for any of these features, it can. It has all of Python, all of CBMC available, but common tropes are sort of summarized in these additional helpers that we have. The next step, of course, then just to come up with a solution, satisfying assignment for these constraints, if possible. If you're unsatisfiable, it depends a bit on the context that we're working in. Usually we leave it to the model to decide whether in this domain or given the puzzle, we would expect that there would always be a solution, or whether no solution is actually a possibility. And in this case, for Logic, for Zero Logic Bench, there was always expected, of course, that there were no samples that had no solution. And so in this case, the model can decide to just restart the process on unset. Same, of course, if we detect any syntax errors. So the only remedy that we take here is just a restart from scratch. We don't take any context with us. We don't try to repair. And when we look at the results later on, I would like to emphasize that again, because what we wanted to explore here in this area is just reformulating the problem and delegating to a constraint solver tool, what is the impact of that? We didn't do any other further optimizations in order to try to boost our scores. We didn't do any test time scaling. We certainly didn't do any fine-tuning on these types of benchmarks. The goal was just to check what is the benefit that you can gain from this. But the result was actually that our agent at the time, even without these additional techniques, became SOTA for this benchmark. And actually, to this day, this is over a year ago when we started with this. Obviously, we only presented a couple of months ago at NeurIPS, but still, in the hardest category of benchmarks, we'll see later, Llama 3.170B, a fairly small and affordable model, is still SOTA in the hardest category of benchmarks, beating all other models using this approach. And that's sort of the argument that we're making overall, is that it's a matter of efficiency, not, of course, you can sort of brute force your way with larger models through a lot of these problems. But if you come up with an agentic use case like this, where you have a tool suited to the purpose, it's frequently a much easier task to teach a model how to use this tool effectively. And we want to extrapolate from that for coding as well. We want to, the next sort of couple of benchmarks we want to go at is LCB, etc., with the argument that if your model becomes excellent at tool use, which I think Copilot, my current company, is an example of that. If your model becomes excellent at interacting with your code and tool use, etc., this can make up for a lot of capabilities that other models sort of like brute force in training. But yeah. It was actually, yes. That is the thing. I wanted to meet with Peter and Ricardo next week. Also, like, we have sort of, and I can talk about follow-up projects later on. But ArcAGI was exactly something where I felt it would fall in the same vein. It was just a matter of representation that we were thinking about. But yeah, it's. Yeah. No, we had a brief look into it, and the idea was, of course, again, if we were to map this to Logic.py, what would that look like, right? What would be the constraints that the model would be using? Would it be like, shape constraints, and like it would basically need to look at the problem and then sort of come up with a constraint for it, derive the mapping between the original ones, and then for the missing one, basically come up with a set of constraints that would then be satisfied by the solver. That was sort of the idea that we had. But the question then becomes, what is the DSL, and how do you avoiding sort of like encoding the problem in the DSL, of course, making the DSL too bespoke to to still claim that this could be general. But yeah, ArcAGI was something that we looked at last year. But I think in the final slide, I'll discuss a few items on follow-up projects, and I don't think that'll be the next one, just because there's specific interest for the other two projects, actually. But we'll get to that in just a second. All right, so just for intuition, what does this look like? The kind of classes that we generate. I said we had a couple of helpers. Many of them are just sort of to make Python data structures a bit easier and a bit less verbose. For instance, like the domain helper that we have is a convenient way of expressing an enum. And you could just the same do this as an enum, but again, we sort of wanted to have it a bit shorter. I already mentioned the unique constraint. There's also like these the maximum sizes of a list. So you can specify a type, not just the type of a house, but also the number of elements this list should have in it. Again, there's other ways of expressing that in Python if you really wanted. You could do this using assertions, etc. But we just went ahead and sort of implemented these additional helpers to make it as easy and as kind of constrained as possible. And given the nature of our backend solvers, at least initially with CBMC, to sort of also enable the model to easily create finite constraints. That's a bit special for Zebra Logic Bench, though, because they're always in finite domains. We have other benchmarks like Folio, where that is not the case anymore. The model just creates universal constraints, and then these things fall away. But the language Logic.py has this ability to express this if the model thinks it's suitable. And the model is also, of course, heavily prompted towards that, to say if you can constrain things just in the data structure, make sure that you do, because it makes the analysis much easier, of course, if your domain already, if the possible values only include reasonable solutions. But ultimately, these are two completely independent tasks. Well, not completely independent. When the model generates the constraints, it is, of course, given the data structure from before, so that it knows which properties it can use to express these constraints over, so that it makes as few mistakes as possible, of course, there. But these are sort of like the kind of constraints that come from this with like all these helpers. And again, syntax is a bit of a topic of discussion. There was a bit of a mix of what is good enough that the model can work with it and efficiently work with it, and what maps easily to CVMC and SMT in the background. And so, for instance, again, the model, if it wants to select any element from the houses in the solution, then it has this non-det helper that accepts sort of any list. Again, there would have been other ways to express this, but also for us, it was actually much easier to map for the backend. So part of it was a mix of how can we make things as easy as possible for the model, and the other portion was how can we sort of not waste too much time when mapping these to the backend. So a bit informed by the backend as well. But these are usually the constraints that the model will come up with. And of course, as most of you will already have had an intuition is, for puzzles like these, where there's either rules to follow or rules for a certain move in a game or steps, the model's task shifts from actually solving this, from actually understanding and reasoning and drawing conclusion, to translating rules. And it becomes a much more suited task for the model, where they perform excellent at, especially when it's just a matter of expressing a domain query by the user into effectively Python. So tasks like this, where it needs to translate that two people live next to each other, that translates to the absolute distance of their house number being 1. Translations like these we see worked extremely well and led to sort of the positive results that we've seen. That's something that we basically benefit from all the coding training that goes into sort of translating human language into programming constructs that map that. And the usual example that I always like to come up with to demonstrate this as well is my favorite one is an issue in the benchmark. So this clue 11 is a problem in the Zebra Logic benchmark. It says the person who loves the spaghetti eater is Peter. This is just a mistake. It should read the person who loves spaghetti is Peter. But here it suggests that there's a sort of a romantic relation between a spaghetti eater and Peter. And the way the model shows to map this, well, what does love mean? Love apparently means that you need to live next to each other. And so again, it has like a similar constraint where it says, well, it needs to be either +1 or -1 from this person's index, etc., from this person's house index, which is sort of a cute way, I guess, to think about how a model thinks love can be expressed in Python, etc. But it's also, mistakes like these are also nice to sort of see which models sort of had a peek at the at the benchmarks beforehand, etc. But interestingly, actually, I don't think I've seen any poisoning there in the models when going through the benchmarks. But yeah, I don't think I should probably go over that again. Recently, we had a couple of very strong models, suspiciously strong models. But yeah, never mind that for now. So speaking of strong models in this context, as I said, when we published this, Llama 7db with our polymath agent was actually SOTA, and still is in the hardest categories to this day, actually. And this is especially striking if we look at where Llama 7db usually is in chain of reasoning, chain of thought puzzles like these, without any agent to support it. We're sort of like in the low 20%, not even reaching 30. And with the agent installed, it immediately becomes SOTA. It has high performance across all puzzle size classes. That's a pattern that we see with other puzzles. That the performance, especially on the Excel puzzles, starts to decrease incredibly quickly, whereas we, for the most part, can keep our performance up. Our issues that we struggle with are sort of different nature. Usually when we fail, and we've seen this actually, then it's usually because of either incorrect constraints. Of course, obviously, the model might produce a constraint that just doesn't reflect what the language says. Fair enough. We've had, especially, not in Zebra Logic Bench, but especially in Folio, which is a different benchmark. Oh, I should have probably explained that. Folio is I'm not sure whether people are familiar with it. It's like a first order logic benchmark. It's meant to trip over models by having sometimes very counterintuitive logic conclusions that can't be drawn from prior knowledge, or sometimes even consciously lead you astray. If you rely on prior knowledge that, for instance, a trout is a fish, that might actually, specifically in this moon logic of this puzzle, in the premise of this puzzle, or in this first order logic puzzle, might actually be exactly the opposite, where it might be a bird and you have to work on the assumption that it's a bird, and things like that, and sort of draw conclusions from there. But yeah, in the what we've seen there a lot is things that we struggle with that are sometimes difficult to formalize. Is, for instance, when, and this is purely probably an optimization of the model as well, and something that we argue that should actually get more attention if we can delegate the task of reasoning to external tools, is, for instance, issues like when the task says that, say, a student, Alice, is an economic student or a math student. And now the model has to decide, well, is this inclusive or is this exclusive or? How do I map this to Python? When the model is done, and for most humans, and many contexts, it's very intuitive that sometimes a student can be in both courses, or a student would only, when it comes to lunch options, or a student will probably only eat one lunch option, etc. But we found that certainly Llama 70B itself was frequently lacking the intuition to make, for instance, that kind of decision. And that's exactly something that if you do tool-aware training, where you sort of realize, well, we are going to delegate this to a tool, we are going to delegate all of the deductions to, say, for instance, a reasoning engine. So we don't need to have that much chain of thought training data. We don't need to have that much reasoning training data. But this kind of training data of deciding is actually these constraints in context could then gain a bit more attention. But yeah, in the results overall, similar to in Folio, much the same. Our agent immediately became SOTA thanks to this. And again, our assumption is that if you want to sort of scale this further, if you wanted to apply TTS, etc., any of the optimizations that we haven't been doing, that certainly GPT at the O3 at the time was definitely doing, with like the high reasoning, using many more tokens that we did, will probably boost these scores even further. With the limited syntax errors, which were about, where we lost about 5%, was just purely the model would produce incorrect Python for one reason or another, and restarts wouldn't help with it. But yeah, those were sort of the very encouraging results that ultimately we weren't even after. Actually, we didn't expect that we would get SOTA on this. We just wanted to see what is the difference for any model, and then translate this work to stronger models, and something like Claude Opus that would hopefully have fewer problems with syntax, etc. But yeah, that is sort of the main drum that we're beating now, is that especially when it comes to tools, yes, people sort of realize that it can make a lot of sense to delegate math to your tools, but we're sort of arguing that many more fundamental tasks people should rethink, certainly when they're in the agentic section, but also in general. Is the task that you're solving actually, do you need to be solving this task directly? Or are you in a position where you can reformulate it, where you can use tools to sort of solve a proxy of the task and still get the same answer out of the model that you want? For us now, looking into the future, that leaves us sort of in a position for two directions. Well, I guess three, but I summarize the other two together. But sort of our follow-up work on this that we're now starting is, A, are there other contexts where we can use exactly this approach, where we can say, well, we rephrase the task and make it easier? One is, for instance, in tool calling, where the intuition is, well, if you have something like TauBench and the model needs to come up with, if you're familiar with TauBench, there's like these retail and airplane benchmarks where you have to basically use a REST-ish API correctly, and you might have to do multiple calls. So your model has to call book a flight, then change class of the flight, and then cancel it eventually based on the user's wishes, etc. And sometimes that requires multiple calls. Sometimes if you need to cancel a flight, you're given sort of the booking number and the name of the customer. You have to realize that you have to call get flight ID with that, and then you have to sort of cancel on the flight ID. They have like these composite nested calls in these benchmarks, and that's usually where the models sort of start falling off very quickly. They seem to be able to reason, SOTA models at this point at least seem to be able to reason extremely well about what a single call does, what like the semantics of this call are. But when they have to sort of chain them together and have multiple steps, that's usually when it becomes a bit more challenging. And our suggestion is, well, if that's the case, can we just say, well, the model just shouldn't do that. It doesn't need to compose. The model just needs to reason over these calls in and of themselves, give us an abstract transformer for each of these calls, and then give us a desired state that it wants to achieve at the end of it. And then we call effectively a sort of a simple program synthesis over these very restricted calls to give you the combination of 2, 3, 4 calls that are necessary to do this. If the model excels at abstracting this correctly, and so it can give us an abstract model of saying, well, this will look up your ID based on the booking number, and we need to get the right ID in order to be able to cancel the correct flight, then we can, of course, easily delegate this to as like not even a CGIS solver, but literally just like a single call in CBMC would be sufficient for this. That's sort of one direction that we thought would be useful. I think, Derek, you posted a paper there?
Yeah, sorry, I can talk about it later. I just wanted to add a note real quick to mention it later, because it reminded me of this.
Excellent. Yeah, looking forward to that. So that's just, obviously, it's just more of the same ultimately. Are there other tasks that we can sort of use these additional tools for it? Another approach would call, well, can we work on a live code bench or something like that? Can we use like the model together with a CGIS engine and have the model come up with invariants, etc. for that purpose, etc. Like have like an optimized loop precisely for that. That's probably a bit of a step further because especially the invariant synthesis, the question becomes then is that at which point is that actually an easier task or is it a more challenging task to use a CGIS engine for synthesis? But that's exactly the kind of things that we're trying out. What would be useful tasks? Is it easy for the model when you're talking about like an agentic tool calling environment to sort of, for instance, if you tell the model, well, give me, for my lighting at home, give me Christmas mood. And then the model only needs to decide, well, what does that mean? It needs to be like these colors need to be there. It needs to be like these patterns, etc. And then what do I actually need to call to make that happen? I'll leave that to the solver. These are like sort of the approaches that will be like in the same vein of simplifying the task or transforming the task for the model. The other direction is, since I mentioned before that for the symbolic puzzles, there's this cell score, where the models get a score if they get partial solutions. And our question was, can we actually use partial rewards during reinforcement learning to sort of improve what the model does? And a lot of people were trying that, but they did it on a syntactic fashion, where they would say, well, just the number of cells that you get correct. If I just briefly switch back here, so just like the number of cells, how many of them are correct, and that's sort of like that determines your partial score. And we thought that might be a bit naive and might lead the model astray, at least when it comes to reasoning, because that might enable the model to sort of reward hack and just provide completely nonsensical solutions that were obviously not correct based on what the clue said. But it allowed the model to fill a certain number of cells correctly, or high number of cells correctly, and easily get a high reward. Our approach was, well, can we actually create an environment where we award points for the model for how many clues it got correct? How many clues did it interpret correctly? Did it respect type information? Did it make any category errors? Things like that, and sort of give feedback based on what a model checker could easily give feedback on. This is obviously it's just sort of a very straightforward extension of that. But as we kept doing that, especially in our context, we generated in RL a lot of interesting trajectories, which we ultimately just fed back into SFT again, which is always a bit of a frustrating situation that we are in, especially with our research engineers. And so the conclusion was, well, could we actually just use our solvers to generate provably correct COT data from scratch, and then maybe run a data augmentation step on top of it? That's sort of the direction that I mentioned that I'm a little bit jaded on, because I've just working with reasoning teams and sort of the way they curate their data, I've just not often seen this kind of basic data translate very well. Where even if you have like the exact same conclusions, if it's not in the same domain, if it's not in chemistry or legal or whatever, even if the, say, legal argument that you're making is actually represented in the formula that you're solving, and even if you run an augmentation step to sort of make it more look like a legal argument, I still I've seen when we integrated puzzle data like that sort of it would help in general out of problem solving or chain of thought problems, but it would drop the actual categories like again like these chemistry or physics scores significantly, which is why I'm of two minds as to whether this is worthwhile. I'm not sure whether this approach can give you the high quality data that you need in the end that makes it worth pursuing. And exchanging other data for it. I mean, it's certainly. I mean, obviously, if you stretch it too far, that's just in the nature of things. I mean, things like legal codes have logical contradictions in them, and that's perfectly fine. That's that's not a problem. But even beyond that, that's why I don't like there's like some training sets that use like SAT solver formulas, for instance, and train the models on those. And that I think is just too far removed from to be still useful in any chain of thought. But even for simpler constraints like these actual just pure implications or things like that, where I think we could generate a lot of interesting data, so the model would not miss a constraint and not miss a constraint implication. But I still think the translation, the transfer to other domains is tricky, and B, for the simple cases where it's close enough, I just think there is enough data on that already anyway, so you're not adding much. And that's sort of like the situation that we have in. We sort of have to decide what would be sort of a more interesting or impactful project, but ultimately we're going to try things out. Obviously, this data generation engine is not going to be that much work, and we can easily just add it to our data mix and see whether it does anything. But as I said, I'm not optimistic on the prospect. All right. So yeah, that's just like a bit of a look in the future. I think the tool calling one is more promising because I think there are a lot of problems where in a tool calling environment, it's easy to summarize the steps in each of them, and it's easy for the model to express a desired state, but it's tricky to combine the 3, 4, 5 nested calls and use the return values and whatever correctly to achieve that. That seems like a more direct, impactful work. And again, it's sort of it goes in the broader theme of us sort of trying to encourage people to consciously use these tools, not just for interaction with the environment, but actually to boost the model's abilities more. All right. I think that was actually the last slide on this topic. So I guess with that, we can probably open it up for questions or discussing the paper that Reka just posted. But yeah, curious to hear what people think about this.
Yeah, sure. Yeah, I just wanted to point you towards this. Also, thank you for the talk. Great work. I'm glad that like people are coming to their senses about like using these tools in like an agentic setting, because it feels like I read so many LLM papers and it's just like, well, we already solved, like we have a symbolic tool that does this. Why are you even throwing an LLM at it? So like, it's really nice to see this.
Well, it's been a source of frustration when working as a research engineer with these teams. I, in particular, remember like our Sweetbench agent had like a step about syntax checking of Python, and their particular issue was that they had too many issues with like tabbing, like just too much indentation, too little indentation, and they were like, well, we could run this through an additional step of the model to just check for that and sort of like maybe identify like additional. And I was like, guys, this is a parser. You're talking about a parser. You can just call a parser for this.
Yeah. So the paper I sent though, so they're synthesizing Daphne objects. So the input is like an API, and then some constraints that you want the object that you're constructing using the API to satisfy.
Oh, nice.
So if you like, yeah, I don't know if you have the paper open, but on page 107.5, yeah, so page 5, I guess. Yeah, there's an example of like some social network kind of API, and then they have some constraints on like the object that gets constructed using that API. And then they want to synthesize like a chain of API calls that constructs an object with those properties. So I don't know, this like this ring a bell when you were talking about like
100%,
tool calling APIs and that.
No, yeah, this is again this approach in general. I think it's we've seen many papers, especially when we work on Logic.py already, doing sort of similar this step of calling out to a solver, etc. Again, direction that we would ultimately like to take it, we sort of see the tool calling as an extremely simplistic program synthesis problem. It would be nice to sort of take it into program synthesis direction, which is sort of what we had ultimately in mind in terms of, well, can we take LCB? Can we have the model sort of formalize this? First of all, what does that do, right? I mean, in terms of formalizing like a pre and post condition, a lot of approaches already just generate more test cases, right? To sort of ask the model to generate more test cases. And we've had previous work where we, for instance, we were in a domain where we couldn't use formal tools, so we just used the fuzzer. But we had pre and post conditions for the fuzzer to sort of guide it and sort of identify did we find a bug or not, and also just not fuzz completely nonsensical inputs, etc. But that's an interesting domain of, that's kind of the same thing. It's just ultimately a massive amount of tests, I guess it is. And how much better is it? Is it easier for the model to create n extremely meaningful tests? Or is it easier for the model to create a pre and post condition with which you can fuzz and sort of replace a lot of these tests? To me, it's not entirely clear, especially when you go into like the LCB direction of, well, now the model maybe needs to come up with an invariant, for a loop invariance or something like that. Is that an easier task now than coming up with 100 tests? To me, certainly for some problems, having worked with Daphne quite a bit, not obvious that using these invariants or pre and post conditions will be an easier task for the model, as we've seen in Logic.py, where it was quite obvious that actually here the models do have a lot of capability that they will perform better than solving the problems actually. But yeah, so it's very interesting for linking that. Thanks, by the way. I think we also don't want to duplicate like that that work there. But like this is sort of our thinking. Can we find domains where this proxy task will be easier? And my intuition is that there's plenty of tasks where the proxy task actually will be much more tricky, even though from a reasoning perspective, this sounds like the right approach. Let's come up with invariants, let's come up with pre and post conditions, but that might actually prove to be a much harder task for the model than just trying out a couple of solutions, generating initial tests, etc. But do you mean that for inference time, or do you mean that for training the model, like doing RL, giving like partial rewards for correct deduction or something like that? Hmm. Hmm. Yeah, so it's definitely what I mentioned before, like there's the idea of generating additional just SFT data that is provably correct, where you will have these correct conclusions, and then run some augmentation step to actually make it sound a bit more natural. When it comes to, we've discussed this with the reasoning team at Met back in the day to sort of, this is something we could do at inference time as well. So have to check the model conclusions. As an enforcement mechanism, yes, I think that's possible. I think there's definitely, but I think there's like the AWS guardrails. There's something similar as well, where sort of the model auto-formalizes specification and then sort of auto-formalizes the response and checks whether it could sort of just gives you additional confidence, even though, of course, at each step it could have made a mistake and these things might not match up, but it gives you additional confidence to go through this formalization step. That's definitely something that I could see in in these constraints as well. But as you say, it might make the problem much more difficult, right? So to come up with the actual constraints, enforcing them, how many mistakes does it make for something that's actually a very easy conclusion? There, I'm not sure of the trade-off. And when it comes for reinforcement learning training, it's extremely tricky with partial rewards. To sort of what a model might make correct deductions all the time that lead absolutely nowhere, that don't help it actually solve the problem. And that is a big issue. How do you reward that? What is the incentive that you give the model there? Yeah. I think I find it interesting, certainly also just in the, hopefully that they will fossilize a little bit in terms of like getting people to use lean and these things and then these but so I think fundamentally extremely interesting and very useful. I've seen a bit of a hype train going on with sort of like things being oversold in a way that's not even useful or necessary, where there was like, extremely impressive work, like some partial manual proofs, which were then completed by the model, which is already great, but then it was sort of like described as fully automated and in like completely unnecessary. That's a bit discouraging. But I think it goes in the same vein. I'm curious. I'm not sure. Obviously, at the time when I left Meta, there was this. Obviously, Jan LeCun left as well at that time, and there was this discussion about world models as well. Obviously, I worked on the code world model, which I think is a misnomer. It's not really, in my opinion, it's not really a world model. It does some things about like trace data and trying to sort of ground up from there, but ultimately it's still a regular LLM learning exactly the same way and not really fundamentally different from how you would train any other state-of-the-art model. But obviously, Jan wants to take this into a whole new direction, and I'm of two minds of that. I mean, with him, you never know. He might just come up with a completely new architecture that might sort of facilitate that. For the current architecture of models and transformers, I have not seen this type of, and just with the question about like these like math startups, like these fundamental building blocks of I'm going to teach it these basic equations. I'm going to teach it basic knowledge about physics, and it will then sort of build on top of that. I have not seen sort of the current architectures performing especially well on this task. They ultimately seem to be more suited at like recombination, as like pattern identification, etc. This fundamental, I understand physics, and hence I can draw these conclusions. Whatever machine would do that, I think would be a different model from what we call LLMs today. And obviously I'm not privy to any information about like the kind of model that Jan is after, but if the intent is to just do that using our current models with just different training data, again with like these ground up, I've not, at least personally from purely anecdotal experience, I've not seen much success in that. So I would be a bit skeptical of these things translating into anything except their domain. There will be great at proofs, etc., but will they help make better chain of thought models? In again, I don't want to exclude it, but certainly when we tried, as I said before, with like puzzles or anything like that, we would only see like the model trying to treat any legal case as a puzzle problem and using puzzle strategies there, and not really, and of course losing massive alpha on those benchmarks. So that's why I'm a bit jaded on the idea, I guess, of generalization, frankly, in most, or at least cross-domain generalization in many of these tasks. No, I mean, honestly, on my end, I had a really good experience with Meta. I mean, that's the thing. I mean, Meta, the AI is going through a lot of transformations. A lot of people had a terrible time there. But I would say at FAIR, and especially the coding team, since it was just integrated into MSL directly, we were spoiled. We were lucky. For me, it was just a matter of timing. Jan had just left, and Microsoft came up with an offer. But I'm one of the few people who has very few complaints about Meta. From what that's not true about everyone, and that's justified so. But I will say, I can't complain about them. I can't. So just to be fair to Meta, this. Mm. Oh, it's really exciting. Yeah, I definitely need to into that a bit more of myself. And all I'm saying is, if it goes again, like the cold world model was an excellent model.